Hi everyone, my name is Cathy Fang, a first-year PhD student at the MIT Media Lab. Here with my co-authors Lingdong Huang and Quincy Kuang, both students at the Media Lab, I'm presenting our paper, An Accessible Three-Axis Plotter for Enhancing Calligraphy Learning Through Generated Motion. We would like to thank our advisors, Zach Lieberman, Pattie, Maes, and Hiroshi Ishii. I would like to begin with a personal story. This is a 7-year-old me. Growing up, I spent many afternoons at my grandparents' house practicing Chinese calligraphy. What you see me doing is observing and copying expert manuscripts. As much as I appreciate the art now, as a kid, I didn't particularly enjoy learning calligraphy because it required repeating over and over the same strokes and characters, and my wrist would be always so sore by the end. Calligraphy learning is centered around the way one controls the brush. Individuals hold the brush almost perpendicular to the paper, which can be difficult posture to perform steadily and consistently. Traditional calligraphic techniques of exposed tips and concealed tips require intricate control of the brush movement and pressure applied to the brush tip. One usually starts by learning basic strokes and the spatial structure within a character. A common practice typically is learning hand over hand. However, a teacher is not always available, and thus the learner will rely on comparing the visual difference between what they write and the expert's writing, and adjust until they have reached a similar result. Writing calligraphy as an art form is one such example of a complex motor task that requires fine motor control. Learning motor skills is essential to our everyday lives, from performing daily tasks to playing sports and musical instruments. Unlike learning languages or math, for example, learning motor skills requires learning movements that are tacit, difficult to capture symbolically, and thus are hard to learn through written representations alone or through observations. We explored designing a system that provide augmented feedback to support learners to learn complex fine motor skills. It is generally accepted that augmented feedback, especially during the beginning two stages of the motor learning process, the cognitive stage and the associative stage, where learners have minimal experience and requires a lot of attention and cognitive load, will be especially beneficial. In HCI, many developed systems that support the transfer of motor skills. For example, in MirrorFugue, it's an interface that visualizes a remote teacher's bodily movement and hand gestures on a piano keyboard. Others were built to provide vibrotactile feedback to help performers gain muscle memory. Most related to our work is DigitalSync, which is a system which a passive exoskeletal glove that help learners learn piano by physically connect the hands of the teacher and the student. Similar to playing the piano, the mastery of calligraphy involves precise control of the hands and pressure on the brush and the speed of the movement. Many handheld tools, not surprisingly in a form factor of a pen, were developed to support human creativity with precision and efficiency. Some directly augment the output, while others directly augment the human. These complement freehand drawing with machine precision, where precision is important for the tasks like creating graphs or a CAD model, but few focused on learning as the goal. So we set out to design an accessible system for novice calligraphy learners to gain additional feedback while practicing on their own, and we have the following design goals. First, our system should be accessible to users, i.e. using off-the-shelf systems, and the effort should be akin to completing an instructable project. Second, the system should help learners to form good writing habits, such as maintaining a steady wrist and holding the brush perpendicular to the paper. Third, learning with our system should be intuitive and engaging, as motivation and positive reinforcement may indirectly improve learning outcomes. Finally, we're avid supporters of open source. We want to make available our tools and designs so that people can remake and build upon our system. Our final system consists of two parts: a software pipeline that converts static images of Chinese calligraphy scripts into movement trajectories, and a 3-degree of freedom gantry that follows a calculated trajectory. The hardware construction of this prototype repurposes an off-the-shelf XY plotter, which keeps the design low cost, allows the user to see the output from above, and does not obstruct the user's bodily movement. Typically, a pen plotter only has a pen up or down function, So to add a movement in the Z direction, a rack and pinion mechanism is added to the servo motor, and we modify the PWM signal for the spindle speed control to control the servo horn position. And during our prototyping process, we found the user might need to have more control, so we added a button to the brush handle such that only when the user squeezes the handle, the machine then proceeds to move. Now I hand it off to Lingdong to describe the software pipeline.
We also developed a series of algorithms to generate toolpaths for the plotter to reproduce given characters of calligraphy scripts. The toolpaths are encoded in G-code and are sent to the plotter via serial connection. As we mentioned, one important feature of calligraphy that actually lacks in most graphical digital representation of Chinese characters is the separation of strokes and their order. The stroke order is not merely a pragmatic rule, but also affects the fluidic aesthetics of the character. To address this, we used an open-source database that provides stroke orders of a standard font. For other fonts, like cursive and semi-cursive, we have a semi-automatic method. Once the stroke order is obtained, we apply adaptive thresholding and denoising. The morphological skeleton of the binary image and the stroke thickness is generated by fitting a maximum inscribed circle centered at each point on the median that touches the outline. The radius of the circle becomes the estimate of the stroke thickness at a given point. Next, we describe a couple of heuristics that enable us to optimize the toolpath for a modified plotter. When plotting with a rigid pen, the tip's position is directly reflected by the handle's position. However, the calligraphy brush tip is compliant and lags behind the handle based on the target thickness. We empirically devise a function that models the distance between a brush tip and the axis of the handle, and we added the distance to the original path in the direction of the motion. Intuitively, this exaggerates the motion of the original path, which compensates for the smoothing of the shape induced by the lag. We also simulate the technique for starting and ending of strokes in calligraphy. A gradually lowering motion in the same direction of the stroke is added before the start of each stroke to prevent the brush bristles from splitting. This produces the look of the revealed tip. For the concealed tip, a backward motion is used. It is well known that human drawers and writers tend to change the speed of movement as they draw different shapes. In calligraphy, the speed of the brush also varies, creating a certain rhythmic pattern. Our observation reveals that the stroke slows at both ends and is fast in the middle, which we model with a section of the sinusoidal curve. We also notice that thinner parts are faster, which we model with a linear function.
Before evaluating how our system is able to support learners, it's important to first understand how well the system is able to recreate the characters. We chose 9 characters from a calligraphy masterpiece by Mr. Yan Zhenqing, as his writing is typically used as a template for the standard font for learners. We employed a series of algorithms that can quantify the alignment or match quality between 2 characters, but in the interest of time, I'll be skipping over this part. Please check our paper for more details, but in essence, a final match distance of 0 means a perfect match. This figure shows the plotter output compared to the original script. While we couldn't claim that our output are nearly as good, it looks visually pleasing. But more importantly, it reproduces many key features in the calligraphy work, such as the embellishment of the stroke endings and the stroke thickness. We also conducted a user study where our main goal is to evaluate our system efficacy at teaching novice users calligraphy learning. We compared our method with watching the video instruction as a video-only control condition. We conducted a counterbalanced within subject study with 12 participants who have never written Chinese calligraphy before. The study consisted 2 rounds of 10-minute demonstration followed by rewrite tasks, where participants were given the freedom to learn and practice however many times they wish. Participants had to learn the characters shi means 10 and ren means people. The two characters, each having merely 2 strokes, combined cover the 4 of the most important fundamental stroke types. There are a couple of criteria in our evaluation. These criteria include the similarity in stroke thickness and the overall composition of the strokes, which we use the same method that we use in our technical evaluation. But one category of the criteria that is hard to tell solely based on the visual output is the process during which the writings occurred. The order of the strokes were written and also the postures of the hand and wrist, which is why we also employed a manual screening of the recording. We performed statistical analysis on the questionnaire data and also thematically coded participants think aloud. We saw that participants were able to write the characters more accurately and also make fewer mistakes in the stroke order when learning with the plotter. We asked them to comment on the importance and usefulness of having haptic feedback. They said, especially for the Ren people character, the change in thickness was shown more saliently, and a plotter would also provide a sense of scale of the movement and demonstrated a close-up of the brush tips. We were also interested in cognitive load. While the plotter did not reduce the participants' overall cognitive load, some mentioned that it was easier to experience the movement from the perspective of the teacher through the plotter. Quote, I found it hard to map to other people, so I tried to overlay myself with the teacher. Questionnaire results also showed that the plotter method is significantly more engaging and fun. Some mentioned that learning from the plotter makes them feel less judged than having a human mentor and less frustrated comparing themselves against the plotter, while others felt that it was harder to relate to the plotter and had a fear of breaking the machine. And all these points point to the nuanced aspect of using machines for instructions. Finally, we would like to discuss findings directly elucidated using our prototype, and we will broaden the scope of recommendations to other systems that support motor learning. First, a couple of words on the limitation of our device. The plotter is inherently limited by its degrees of freedom, and currently it only follows predetermined movement that the learner passively follows. Beyond learning other types of calligraphy, the brush could also be replaced with other tools where the learning of depth is also important. Besides motor learning, our system can also be used to represent the presence of a person across distance and time, like Tom Riddle's diary in Harry Potter. Now I'd like to share insights that are also generalizable to other fine motor tasks and multimodal learning. First, it's important to define the learning goals, as having too many focuses, especially in a complex task, can overload, especially a novice learner. So for us, we help them focus first on the change in the brush height during writing. Spatial collocation is also an important aspect, as a shift in the spatial orientation introduces additional cognitive load. Our system allows the learner to perceive feedback in the same coordinate frame, so there's no mental rotation needed. Temporal coincidence of the system allows the learner to directly connect the change in the strokes to the change in the Z depth more intuitively. But on the other hand, if there's a misalignment between the machine and the human intention, it can also lead to confusion and disruption. In other words, it impacts the user's sense of agency. During motor learning, the learner's mental model of the task adopts based on the feedback they receive. However, if there's a lack of participation, learner cannot identify the consequences of their actions clearly. Please see our paper for the full details. We would also like to thank Professor Ken Nakaaki for his guidance throughout the project and the study participants for their time.